All right, guys, so let's jump in and talk about some thermodynamics and energy and disorder. All right, so we're going to be looking at entropy and enthalpy and a couple other things in this lecture. So let's start with some definitions. All right, first, thermodynamics. That is the study of the flow of energy during physical or chemical changes. And we've been talking about some thermodynamics already. We looked at specific heat. We've looked at a couple things like enthalpy, and now we're going to look at entropy. All right, we're going to talk about the system. You define the system as the scientist. It's whatever we are studying. The surroundings is everything else in the universe. It's defined by what is not in the system. Okay. The interface is the boundary between particles or the boundary between a system and the surroundings. It can be either one. So we can look at it as a really microscopic kind of microcosm, right? Just the point where two particles touch, or it can be like if I'm studying a coffee cup, it could be where the cup touches the air, something like that. Okay. And the final thing we're going to look at is entropy. Okay, that's the newest variable we're going to have. We abbreviate entropy, or the variable that we use for entropy is S, capital S. And we're also going to talk about something called a state function. And a state function is let's see if I can move this thing out of the way here. Yeah, there we go. Sorry about that. A state function is a variable or a property of a system where the value is independent of how we measure it. And we'll get into that in a minute. All right. So those are some definitions we're going to need. Now, where do we see thermodynamics in nature? All right. Well, the first thing we notice is that systems always tend towards the minimum energy. Right. And we can use that fact to predict different outcomes, different behaviors. All right. And we'll see that in a moment. We're going to find that systems tend towards maximum disorder. And the more possible arrangements a system has, the more disorder is present. And disorder, don't think about disorder in terms of like unfolded laundry. We're talking about the number of different ways you can arrange a set of particles, right? That's really what we're looking at there. We call a possible arrangement a microstate, and we abbreviate microstates with a capital W, right? And we'll see that again in a minute. Now, all of the tendencies that we look at in thermodynamics are related to statistics and to probability. All right. And the thing that we find is that lower energy means the system is less likely to change, and less likely change equals more likely to be stable. All right. There are more situations that we find in nature that are considered disordered than ordered. Okay. And if we're looking at reactions, reactions are going to occur because of either one or both of these two tendencies in red. Okay. That's what we're looking at in thermodynamics. So, what is entropy? Let's take a moment and talk about this new term. Entropy is the randomness or the measure of randomness in a system. It's related to three modes of motion in molecules. We have translational motion, vibrational motion, and rotational motion. All right. And so I think I have a picture of this in a minute. I do. But translational motion is when a molecule actually moves from point A to point B through space. Vibrational motion is actually where the atoms themselves are kind of moving in place, but they're vibrating, they're moving back and forth. And then rotational motion is when, like, let's say we have a water molecule and it's rotating about an axis. So, like, my two hydrogens are side to side, and now they're pointing right at you, something like that. We can picture microstates in using dots or using any kind of drawing that um, illustrates where our molecules are at a given moment. So instead of thinking about it as vibrational or rotational motion, sorry, in this picture here, we're looking at it as translational. We're looking at where are the atoms moving. So in the first picture in A, all four of our particles are on the left side of the box, right? In B, we have all the different ways where one of the particles could be on the right and three of the particles could be on the left. You can see that there are more possible arrangements for one particle to be in the box on the right compared to A, where all of the particles are on the left. There's only one microstate where that happens. In C, we have all the possible arrangements for two particles on each side of the box. D, we have one particle to the left and three particles to the right, and E, all four particles on the right. Now you'll probably notice something, okay? There is a statistics curve, like a bell curve here. It's just on its side, right? And we see that there are more possible arrangements in C than anywhere else. And so if you were to randomly sample this four particle system, the most likely thing for you to find will be C, right? Because there's the most common microstate. So think about a bell curve. That's a terrible bell curve. Let's redraw that. Go. Remember that in a bell curve, the middle, right, is the average, is the most common value. Okay. And if you've done a little bit of statistics, and I don't know how much statistics you guys have done in math class, but there's about roughly, I think it's 67%, I believe that's the number, of all of the microstates are contained, or all of the values in a population are contained within one standard deviation of that mean value. So if you've done some statistics and that means something to you, great. If not, don't really worry about it. Now, when we actually calculate this in chemistry, we use factorials. Right? That's the exclamation point on your calculator. And if you take my AP class, we'll actually calculate some of these things. Okay. So in this image, we have 16 possible microstates. And again, that would mean W equals 16. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. That's what we're counting. So entropy is the description of the randomness. Once we identify the microstates, we can actually calculate the entropy. And the formula that we use for that is S equals K ln of W. And ln is natural log. All right, that's another button on your calculator there. K is Boltzmann's constant. All right, it is 1 point, I think that should actually be 38. I just found a typo. I'll have it here later. Oh, where's it at? Hold that thought. Yeah, that should be 38. Hmm. Sorry. Another typo to fix. 1.38 times 10 to the negative 23rd. Okay. Joules per Kelvin. W, again, is the number of microstates. And S is going to be entropy in terms of joules per Kelvin. All right. So we can actually calculate the entropy of that system. If we wanted to from the previous problem, we would say 1.38 times 10 to the negative 23rd times the natural log of 16. And that would give us S. And remember, the unit for S is joules per Kelvin. That's what we're after there. All right, so here's the picture of the vibrational, translational, and rotational energy. So if you wanted to look at it, there it is. But remember, those things are what's going to give us different entropy, or sorry, different microstates that we'll use to calculate our entropy. So I talked about statistics a minute ago. I talked about probability. And basically, let's kind of look at this in terms of a macro state instead of a micro state. So if I have bricks and I just throw bricks over my shoulder, which of these two pictures is obviously the more likely way for things to fall? I mean, hopefully you know that it's going to be this one. This is more likely. There's only one microstate where I get this wall. So over here, W equals 1. But on the right, I have many, 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 many different microstates, right? W is like next to infinity, right? It's approaching infinity. Because to get a pile of bricks, it doesn't matter where each brick is or the arrangement of brick A compared to brick B. It just has to be an unorganized pile of bricks. So there's more entropy on the right, and we know that systems tend towards maximum entropy. And so we look on the right and say, yeah, that's how the bricks are going to fall. They're not going to fall to the left. Now, that's a statistical probability. It means that there is a very small chance that I could get the wall on the left, but it's such a small chance that it is unlikely compared to the pile on the right. Now, in chemical entropy, can look at that like this. So on the left, I have a diatomic system. All the molecules are paired. And on the right, I have monatomic atoms just floating around. And if we assume these are both gases, they're both at the same temperature, then if I ask you which one has lower entropy, it'd have to be the one on the left, because the one on the left has some more organization, right? Everything is organized into pairs. The one on the right is not. These guys can go, like this guy could go this way, and he could go there, and they could go that way, and they could all move. And this one, these two have to move in the same direction. And so there's more organization in our diatomic system than in our monatomic system. Okay. In other words, there are more microstates on the right than there are on the left. Okay, that's what we're looking at there. Now let's look at that in terms of phases. So gases on the left have the greatest amount of entropy because they have the least amount of order. You have the most microstates belong with the gas. W is really, really big, all right, with our gases. Liquids are going to be in the middle. There's still a lot of different microstates, right? These things can still move and trade and dance all around, right? But it's not quite as good as the gas is. All right, let me get a different pen. All right, so all of these guys, they can move, trade spaces, all that, but not as much as this guy, right? He can go all the way over there, unobstructed, all the way over here, right? All the way up. Lots more entropy in the gas. Now, in the solid, you still have vibrational entropy. So they can move a little bit, right? They can move left and right and push against each other. You have a lot of order on the right, so you have much less entropy. So entropy increases with what we call molecular freedom of movement. The gas has a very high freedom of movement. The solid has a very low freedom of movement. So remember, S is entropy. So the entropy of a gas is greater than the entropy of a liquid, which is greater than the entropy of a solid, given the same conditions, right? Same temperature, same pressure, all that stuff. All right, let's look at entropy when it pertains to temperature. So we know that as temperature increases, molecular movement increases. So we would expect as temperature goes up, entropy goes up. And that's exactly what we see on this graph. So for a solid here on the left, as the temperature increases, you get greater vibrational movement. You get greater translational movement, right? The molecules are moving just a little bit more, right? They're kind of vibrating in place and they get hotter and they get hotter and they move faster. When you start to melt, right, remember that melting involves an increase in energy, but not an increase in temperature, right? 0 degree ice can also, you can also have 0 degree water because they're phase changing, but the entropy is going up very quickly. Right? You're looking at a liquid. As you heat it up, the entropy increases, right? When you start to boil, you get a very rapid increase in entropy. And then as you heat up a gas, the same thing occurs. All right, so we see that as temperature goes up, entropy goes up. So what does this imply about system changes? How can we use this to predict things? Well, the more particles I have in a system, the more microstates there are, the more entropy there is. So if I'm comparing two systems and one has more particles than the other, if everything else is equal, the one with the more particles has greater entropy. If I have a higher temperature, well, the more temperature or the higher the temperature is, the more energy states there are. Remember our Boltzmann distributions of temperature, right? At a low temperature, more of the molecules are at this temperature, right? But the range is shorter, right? Greater range, greater temperature. Okay. Greater temperatures, more entropies. All right. What about less structure? So here we're talking about phases. So the greater the freedom of movement, the less structure there is. The greater the freedom of movement, the more microstates there are, the more entropy there is. All right. So those are all things we can use to predict outcomes about entropy and about systems that we're studying. So now let's look at the first law of thermodynamics, and let's take some of these observations and actually compare them to the laws of thermodynamics that we see in chemistry. So the first law is the law of conservation of energy. It says that energy cannot be created nor destroyed. It also says that the total amount of energy in the universe is constant. It does not change. And since that is true, the change in the energy of a system and the change in the energy of the surroundings must equal zero, right? The overall net movement of energy has to balance out. Well, that means that we can transfer energy from the system to the surroundings, or we can transfer energy from the surroundings to the system, but we can't create new energy, right? We can only move energy around. Now, the math behind the first law looks like this. E equals Q plus W. E is energy, Q is heat. It's the exact same Q that we saw in like Q equals MC delta T in specific heat, or Q equals negative delta H with enthalpy. And W, lowercase w here, is an amount of work. Okay, so remember that Q can equal negative H, all right, from our discussions of enthalpy and Hess's law. All right, just kind of keep that in mind. Now, before we go and look closer at this E equals Q plus W, let's take a moment to talk about the difference in a state function and a non-state function. So a state function is a property of a system where the value is independent of the way that you measure it. So state functions are things like temperature. It doesn't matter how you measure the temperature is the temperature. Okay. The volume, always constant. All right. It doesn't matter how you measure the volume, you're going to get the same outcome. Like, what do I mean by that? Well, let's say we have a cube, right? And we do the length times the width times the height. That's going to give me the volume. Well, let's say instead of doing it with a ruler, I wanted to measure displacement. So I had a graduated cylinder, I measured the volume, I dropped the cube in, I measured the new volume, I subtracted it. It doesn't matter that I've measured it two different ways, I'm going to get the same volume. It's a state function. Pressure, same thing. It doesn't matter if I measure it as a partial pressure compared to atmospheric pressure, or if I measure it with a pure system with just a barometer, or however I get there, I'm going to get the same pressure. Same thing with energy. It doesn't matter how you measure it, energy is a state function. Entropy is a state function. All right, notice all these variables have capital letters. And not always, but oftentimes when you see a capital letter, you can assume, hey, this might be a state function. That's a good place to start. Let's look at non-state functions. Time is a non-state function. Depending on how you measure time, you can actually get some different values. So things like time dilation and the relationship between the speed that you're moving at, the speed of the object you're measuring, those things can actually affect measurements of time. Heat. Heat depends on how you measure it, right? Heat is not the same thing as temperature. So those two things are not the same, right? Temperature is a state function, whereas heat is a non-state function. Work. Work is also a non-state function. So what is a visual that we can put with that? Well, altitude, right? The distance that Mount Kilimanjaro is from the bottom to the top, that is a state function. The altitude doesn't change. It doesn't matter how you measure the altitude. It is what it is. The distance you have to hike in order to get from base camp to the summit, though, is a non-state function. Let's say you followed path Y. You would walk much further than if you, excuse me, gracious, if you followed, we'll say path Z, right? There's path Z. Now, path Z might be a little bit more strenuous, right? It's got a nice straight stretch there, and that looks a little steep, and that looks rough. But depending on how you follow it, right, X, Y, or Z, you might walk a different distance. So the distance you're traveling depends on your route, but the altitude of Mount Kilimanjaro doesn't change based on how you get there. So that's the difference in a state function and a non-state function. All right, let's look at it in terms of energy equals Q plus W. So here I have two batteries. They're both 12-volt batteries. The first battery, I'm going to put it into an airplane, and I'm going to use the power in that battery in order to fly. So here, the 12 volts, which is the energy, is equal to Q, the heat given off by the battery. And we know that as you use the battery, it will warm up and will waste some energy in the form of heat, but we'll get a lot of work out of it. So work is going to be a pretty big number here. Now, let's say we take the same battery and we stick a wrench across it. Well, now I still have 12 volts. 12 volts didn't change. But in this case, Q, the heat is going to be really high and work is going to be really small. I'm not getting any major work out of this. Okay. So it doesn't matter how I measure the energy, whether I measure it in what it can do in the airplane or what it can do with the wrench across the posts, I'm still going to get 12 volts. The thing that is going to change is the Q and the W. All right. So energy out is a state function, but the Q and the W are non-state functions. We get two different numbers based on how we use the battery. Now let's look at the second law of thermodynamics. It says that for any spontaneous change, the entropy of the universe must increase. So the delta S of the system, the change in entropy of the system, plus the change in entropy of the surroundings is greater than zero. That's what the second law tells us. It also tells us that if you have the entropy of a reaction, that's going to equal the entropy of the products minus the entropy of the reactants. Okay. And unfortunately, the second law of thermodynamics tells us you can't break even. So, like, there's no such thing as a perpetual motion machine. That's not something that you can have. All right. You can't get something for nothing. That's another way to phrase the second law of thermodynamics. Okay. And again, it means that if there is a spontaneous change, the entropy of the universe must increase. Right? And a lot of times when we look at spontaneity, we're talking about Gibbs free energy in chemistry. And so if Gibbs tells us that, hey, this is a spontaneous reaction, then we can expect the entropy of the universe to increase for that reaction. All right, the third law. The third law is probably my favorite law. It's the one that has kind of a cool math moment where we can tie in the Boltzmann equation to something that is now in this law in front of us. So the third law says the entropy of a pure crystalline substance at absolute 0 Kelvin is zero. So how do we get there? Well, entropy is Boltzmann's constant times the natural log of the number of microstates. There's Boltzmann's constant. There's a number of microstates. And at 0 Kelvin, right? Kelvin measures molecular movement. That's what temperature is measuring. At 0 Kelvin, what we're saying is the molecules are not moving. There's no vibrational energy. There's no translational movement. There's no rotational movement. Nothing. The elements, the atoms are stopped. They're frozen in a spot. They're not moving at all. And if they're not moving, there's only one microstate. So W equals 1. So if you do the ln of 1, you get 0. So K times 0 is 0. So entropy would be equal to 0. Now, the second law tells us that entropy needs to be increasing for spontaneous processes. So we're not going to get to absolute 0 spontaneously. I can tell you that. And I think it's worth pointing out here that it's really hard to get all the atoms in an object to stop moving. So getting to absolute 0 would be very, very, very difficult. Now, there are scientists who have worked on trying to get gases to absolute 0. They've gotten very close. They've gotten to like tenths of a degree Kelvin, but they haven't ever got to absolute 0. And if you do get there, well, that system will have an entropy of 0. That's what that tells us. That's the third law. So that brings us to Gibbs free energy. And Gibbs takes enthalpy and temperature and entropy, and it puts them all together to give us Gibbs free energy. And in case you're wondering, Gibbs' first name is Josiah, and his middle name is Willard. Josiah Willard Gibbs, and he named Gibbs free energy after himself. Smart guy. So delta H is enthalpy, T is the temperature in Kelvin, and S is entropy. Now, this is worth noting. If delta G is negative, then you will have a spontaneous reaction. It means that there's energy that is available to drive the reaction forward. Okay. So if delta G is negative, the forward reaction is spontaneous. If you get a delta G that's 0, then the reaction's at equilibrium. And if you get delta G is positive, the reaction is going to be spontaneous in the reverse direction. So from the products to the reactants. Give me just a second. I need to plug in my computer. There we go. Didn't want it to go to sleep on me. So, where do we see spontaneity? How do we look at that? Well, let's check it out on a graph. Okay, so we're going to put delta H and delta S on my axes. All right, and we're going to look at this in terms of positive and negative, because in first year chemistry, we look at this, we kind of take a surface level approach. Hey, can you make some predictions? If you take AP, you'll see this again. You'll have a nice foundation, and we'll actually do some of these more complicated calculations. But let's just look at it. So if you have a negative delta H, right, and a positive delta S, then you are not spontaneous at any temperature, right? If you have positive delta S and positive delta H, then you're spontaneous at high temperatures. If you have a negative delta S and a negative delta H, then you're spontaneous at low temperatures. And if you have a positive delta H but a negative delta S, then you're spontaneous at all temperatures. Okay, so this is a good little chart that will help you kind of keep those things straight. It's good for making predictions, but I'm not going to actually have you do any crazy calculations with that. All right, so that wraps up our look at entropy, okay, and thermodynamics. If you have any questions, let me know, and I'd be glad to give you guys a hand. Other than that, I'll see you in the next video.